Hello, this is the fifth video in the third Matrices series for OCR IS Core Pure Further Maths. It will consider the links between inverse matrices and transformations. Multiplying by an inverse matrix may be viewed as matrix division in terms of reversing the effect of or undoing a linear transformation represented by multiplying by a 2 by 2 matrix. Let's look at this example. A point P is mapped to the point Q, 4 minus 2, under the transformation represented by 2 by 2 matrix A, 2, 4, minus 1, 3. We're asked to find the coordinates of P. We know then that AP equals Q, and that therefore, if we pre-multiply by the inverse of A, we would get a to the minus 1 AP equals a to the minus 1 Q. Or in other words, using the fact that a to the minus 1a is the identity matrix, P will equal a to the minus 1 Q. Well, a to the minus 1, or the inverse of a, is going to be 1 over the determinant, which in this case is 2 times 3 is 6, minus 4, so in other words 10. And we're going to swap the a and d around, and we're going to change the sign there, B and C. So if we then look at a to the minus 1 Q as being that times 4 minus 2, then we will have 1/10 of 3 4s are 12, minus 2 would give us 10, and minus 4 times 4 is minus 16, minus another 4 is minus 20. As you can see, that would give us 10 over 10, or just 1, and minus 20 over 10 is minus 2. Therefore, P is just the coordinates 1 minus 2. We know that the relationship t to the minus 1 equals t to the minus 1, 2 is the identity matrix for 2 by 2 matrices. And we have looked at some simple transformation matrices already, those being reflection, rotation, enlargement and stretches, and shears. Now, sometimes it's easy to find the inverse matrix by just considering the inverse transformation, probably from a geometric point of view. For other matrices, we would use the standard result that we've already come across in previous sessions. Let's consider these reflections. So reflection in the x-axis, or in other words in the line y equals 0, if we were to undo this, we would simply reflect back again. So the inverse will be exactly the same. You will note here that the determinant is minus 1, something we looked at in the previous video. For reflection in the line y equals x, then as a reflection, the inverse will be a reflection back in the same line. Again, the determinant is minus 1, as we saw on the GeoGebra in the last session, and we know that therefore the orientation will be reversed. You may wish to pause the video now and try some other reflection examples for yourselves. When we consider rotations about the origin, a rotation by 90 degrees about the origin in anti-clockwise direction will be undone, or the inverse will be a rotation of 90 degrees about the origin in the clockwise direction. Here you'll see that the determinant is 1, or positive. Rotation by 180 degrees about the origin also has a determinant of 1, I am positive, so the orientation for both images will be the same as the objects. You may wish to pause the video now and try some other rotation examples for yourselves. You may want to take a moment to pause and check these inverses. When we consider the inverse of a horizontal stretch by scale factor k from a geometrical point of view, we'll probably realise that it is a stretch with scale factor 1 over k that is the inverse. So let's put the factor of 1 over k outside, and then we would have 1, 0, 0, k. For an enlargement by scale factor k, again we would expect the inverse to be an enlargement by scale factor 1 over k again, but in this case we would have 1 over k squared k 0, 0, k. So we may wish to think of it like that. Which of course reduces to that. For a shear of the x-axis invariant or parallel to the x-axis, we already looked at an example in previous sessions of a type 10, k1, and we noted that the determinant was 1 and therefore there would be no change in the area between the object and the image. The inverse would be form 1 minus k, 0, 1. You may wish to pause here and try out some Shears examples for yourselves. Just to remind you, in an earlier video we found that the inverse of a matrix product could be found using ab to the minus 1 equals b to the minus 1, a to the minus 1. Again, let's think of this in terms of successive transformations. For example, if we apply a rotation followed by a reflection, then to undo this, we would have to undo the reflection first and then the rotation. The following simple transformations in 3D were covered. Reflection in one of the planes z equals 0, or the xy plane, y equals 0, the xz plane, x equals 0, the yz plane. We also looked at rotation of multiples of 90 degrees about one of the axes. We can think of inverse transformations in 3D as being related to inverse matrices, just as we did in 2D. So, for example, the matrix M equals minus 1, 0, 0, 0, 1, 0, 0, 0, 1 is a reflection in the yz plane, as seen by the brown unit cube reflected to being the green unit cube. The geometrical inverse of this transformation would be a reflection back in the yz plane, and you may wish to check this for yourself by multiplying. This is the last video of this third matrices series.